Okay, next we're going to apply some of this linear algebra stuff to our Markov chains. So let's look at our transition matrix A, where the columns, every column in A, the columns I'll add to 1, because that's the probability of leaving basically any state and going to each other state. Okay, now let's say V is an eigenvector with eigenvalue lambda. Then that means AV equals lambda V. And then if we applied A n times, then that would be the same as multiplying by lambda n times. Okay, now we cannot have this going to infinity, because the columns of A add to 1, so if I multiply by some state, I'm not generally going to increase the values in V. And actually, the V's that we're going to use will have the values in V adding to 1, so certainly not going to increase. So because of that, then I cannot have the absolute value of lambda or the norm of lambda if lambda is complex, because sometimes we will have to allow lambda to be complex. I cannot have the norm of lambda be greater than 1, otherwise this thing will go to infinity if as n goes to infinity. So I must have the norm of lambda less than or equal to 1. And we saw in our example from last week that we are going to have one eigenvalue of 1, so we'll call that lambda 1, and then all the other eigenvalues will be less than 1. Or if they're complex, they'll have norm less than 1. Okay, so let's look back at the weather case. Which was our example from last week. Our transition matrix was 1/2, 3/10, 1/5, and then 0, 1/2, 1/2, and then 1/20, 1/10, and 17/20. That was our transition matrix from last time. And then we can find you can do this by hand, or for this class, if you put this into either something like MATLAB or Mathematica, or it's just some online eigenvalue calculator, I'm okay with that. We're not testing your linear algebra necessarily, unless the homework problem specifically says to do it by hand, which you do know how to do. And then this gives you, there's an eigenvalue of 1 with eigenvector V equals 5, 13, 20. And you might get some scalar multiple of this. If you scale the eigenvector up or down, it's still an eigenvector, because it'll still satisfy this equation. Like if you double V here, then this thing is still satisfied. Okay, so this is very big. It cannot be a state in our problem. We're not going to have the weather be sunny with probability 5. That's greater than 1. So we're allowed to scale up and down, so we'll just scale. So, oh, sorry. This was actually wrong. This was supposed to be 50. Apologize for that. So let's add these up. This adds, we want it to add to 1. This actually adds to 68. So we're just going to scale it down. We'll call this like V hat or something. That's not the one we want. The one we want is V. We'll scale this down by a factor of 1 over 68, and now these things will add to 1. 50 over 68. And by the way, if we looked back, okay, so this is about 0.074, 0.191, and 0.735. And if we looked back at our matrix, we had calculated like a to the 30 or a to the 100 or something, and these looked approximately like these numbers. These started looking like this, 0.191.735, and it was like this in all three columns. And this generally will happen as long as we have distinct eigenvalues. Okay, so why is this true? A to the 100, or some big power, will start to look like this. They might have still been 1,000th off, depending on how big we went. Okay, so why? Well, a to the n, we said in the previous video, was this matrix V, which is all the eigenvectors listed as columns, times this matrix lambda to the n, which has is a diagonal matrix with the eigenvalues on the diagonal, V inverse. And then as n goes to infinity, this lambda, well, it has the first eigenvalue is 1. Oh, where are we? Up here. First eigenvalue is 1. All the other eigenvalues are less than 1 or have absolute value or modulus less than 1, depending on if we're complex. Then, raising that to a big power, that first eigenvalue will be 1 to a big power is 1. And then all these other smaller ones are going to go to 0. Probably should not use n for both of these. Let's call this m. Apologize for that. Okay, so A is now an m by m matrix, and n is the power that we're raising to. N is going to go to infinity. Do not do that. Do not use two different, the same letter for two different things. Okay, so all of these other smaller eigenvalues raised to some big power are going to go to 0. So this is the matrix with 1, 0 in the top left and zeros everywhere else. And then we have V times that matrix times V inverse. And if you check this out, check out a formula for V inverse. This is going to be this eigenvector V1 scaled to have the entries adding to 1. So the cool thing about the steady state, as we saw in the weather example, it didn't matter if it started sunny or rainy or overcast. It eventually went to all the same probabilities. Why is that true? Well, let's start with some vector v0. And let's say so now let's be in the three-dimensional case. So v1, v2, and v3 are the eigenvectors. And we'll assume they're nice, they're linearly independent and everything. There is a way to do this when they're not linearly independent, but you have to be a lot more subtle with your math. Okay, so since they're linearly independent, they span the whole space. We're in a three-dimensional space now. Then v0 can be written as a linear combination of these vectors. Okay, and then if I look at Vn, after n iterations, this is an times v0, a to the n, and then the 0 is not a power. Well, if I apply a to v1, that's the same as applying lambda 1. And if I apply an times to v1, that's the same as applying lambda 1 n times. So this is what we get. C2 lambda 2 to the n v2 plus C3 lambda 3 to the n v3. And then what happens? Well, again, we have lambda 1 is 1, lambda 2, I'm going to write the absolute values this time, and lambda 3 in absolute value are less than 1. So as n goes to infinity, these terms drop out, and we're just left with, and this lambda 1 to the n is 1, so this goes to C1 V1, which again is a scaled eigenvector v1. And it's just going to be scaled so that the sum is 1. So no matter what vector I start with, the n vector is going to be a scaled version of that eigenvector corresponding to eigenvalue 1.